session on K omega turbulence model. In the last session, we covered extensively the K epsilon turbulence model. Now we'll go to the K omega turbulence model. Earlier, we have defined what is omega. Omega is specific dissipation, turbulent dissipation per unit kinetic energy, right? So this K omega turbulence model was initially proposed by Kolmogorov, right? But he did not mention its two equation form, right? In 1940s, contemporary to Prandtl's thing, he proposed something about omega from statistical analysis, but in a computable form, he did not prescribe the two equation, right? It was originally the Wilcox, okay? There is a book called Turbulence Modeling for CFD by Wilcox. David Wilcox, he prescribed this K omega model, right, in 80s. Okay. How this K omega model looks like? This omega is epsilon by K, okay, but exactly not epsilon by K, there is some proportionality constant, right? Dimensionally, the omega is epsilon by K, there is some proportionality constant. Wilcox taken it as beta star, right? And this beta star is nothing but your C mu. The coefficient that we are using to calculate eddy viscosity in the K epsilon model, this beta star is close to C mu, that is 0.09, right? For the standard K epsilon model. So this is called omega. This is how Wilcox defined omega. Not exactly K by epsilon. K by epsilon, they scaled with some parameter that is called beta star, right? So now this is the governing equation. These are the governing equation for Wilcox K omega model, right? So what happened? What are the terminology in this two equation model? Let's find out. This is the K equation. As usual, the left side represent the advection, right? Then this side represent the diffusion, laminar diffusion, but plus the turbulent diffusion, right? There are few additional terms. This is the production term, right? This is a turbulence production because of the shear. If there is buoyancy, we can add also turbulence production due to buoyancy. There is a dissipation term, right? Omega in terms of omega. Similarly, in the omega equation, there is a dissipation or destruction term in terms of omega square. There is a production term, right? There are some other coefficients, right? These constant coefficients are prescribed: beta star 0.09, beta 1 3 by 40, gamma 1 5 by 9. So this model is closed in this form. And once this model is known, right, you solve value for K, you solve value for the omega. Once the K and omega both are known, then the eddy viscosity is the ratio of K to omega. Clear? But what the issue with this model? Wilcox developed this model. This model performs well close to the solid wall, but extremely sensitive to free stream velocity. Okay, so let's see what is free stream velocity, right? Suppose you are on boundary layer, okay, suppose, yeah, sorry. What is free stream velocity? Let's discuss it. Okay, suppose this is my flat plate. Okay, there is a flow over a flat plate. Boundary layer developing is like this. This K epsilon model predict well when it comes to the flow measurement near the solid wall, but it is extremely sensitive to the free stream velocity. That is a uniform velocity outside the boundary layer. That is the free stream velocity. Suppose you increase slightly perturbation to the free stream velocity, you increase little bit free stream velocity. Suppose this is u infinity, then you add it u infinity plus 10 to the power minus 6, very small amount, add it. then result was drastically changes. This model is drastically sensitive. This is how it looks when there is a slight change in the free stream velocity. The kinetic energy scales square of the free stream velocity. If there is a slight change in the order of 10 to minus 6, minus 8, minus 10, you can change the mu t is nothing but the ratio of eddy viscosity to laminar viscosity. The ratio of eddy viscosity to laminar viscosity. Okay. That drastically order change 500 to around 300 to 250. That drastically changes with this Wilcox model. Right? Wilcox prescribed this model in 1988 when it found with free stream velocity this model drastically gives the deviation. Right? Then subsequently what happened? Wilcox tried to fix those things. Right? How he fixed those things? He put the definition. Okay. Then there is called cross diffusion term. He add this cross diffusion term to the omega equation. What is the cross diffusion? The diffusion of the omega that is affecting the k and the diffusion of the k that is affecting the omega. So the multiply by this term called dk by del xj, del omega by del xj. So this two, the product of these two term, okay, multiplication of these two term, then Spiegel actually recommended it to add it to Wilcox model. Subsequently, Wilcox added these two term, okay, into the omega equation to correct the free stream sensitivity. Right? Once this term is added, the cross term diffusion term is added and divided by 1 by omega, the performance of the k omega model improved little bit compared to the sensitivity to the free stream. Right? The model predicts well close to the boundary, but it was extremely sensitive to the free stream. Now the performance improved little bit. Clear? Now the performance they improve little bit after adding the cross stream term, right? Cross diffusion term. Then subsequently, okay, this is Mentor, Florian Mentor. This guy is with ANSYS. He developed K omega SST model, right? Someone was talking about he was doing K omega SST. What exactly this SST model is doing? This Florian Mentor, okay, what he did? So he developed the modified K omega model, where in the Wilcox model, this parameter was somehow constant. They fix it. But the idea of Mentor to blend K epsilon model and K omega model. What? The K epsilon model performs very well in the free stream region. K epsilon model performs very well in the free stream region. It performs very bad in the near wall region because of the wall function and all those things. K omega model, they performs very well near the wall condition. They perform poor in the free stream condition. Then the idea of the Florian Mentor is to blend these two model, okay, so that there is a new model, okay, which perform close to the wall, it will perform K omega, away from the wall, it will perform as it is a K epsilon model. The philosophy of that to developing the SST model, sales transport model, is that close to the wall, the SST model should perform as it is K omega model. Away from the wall, the model should perform as it is K epsilon model. To do that, he prescribes some blending function. Instead of having a constant coefficient, this function blends the value from the wall to the core based upon the distance from the wall, right? So what happened in the Wilcox model, okay, this value, what Wilcox was predefined over here, yeah, sigma q1, beta star, beta 1, gamma 1, what Wilcox were prescribed earlier. Okay, that thing, after adding the cross stream term also, this guy Florian Mentor, he used a blending function. What is that blending function? The blending function is f1 and f2. Just like you are doing linear interpolation, this phi, okay, is the interpolation of phi1 and phi2. One is close to 1, one is if it is not close to 1. Okay. Then what are this phi1, phi2? This phi1 can be my sigma k1. This phi1 can be my sigma omega 1. This phi1 can be my beta 1. Phi1 might be gamma 1, like that. Similarly, phi2 can be my beta 2, gamma 2, like that. Right? What happened in this model? The coefficients, they are not any constant value. Rather than one, Florian Mentor calculated this blending function f1 and f2. I'll show you what the blending function is, how it looks like. He calculated the blending function. That blending function explicitly depends upon the distance from the nearest wall, right? Once the blending function is known, he blend this parameter. Okay, he at a particular grid. First, he evaluate the blending function. Once the blending function is known, he find what is the value of beta. So that how beta 1 into blending function plus 1 minus blending function into beta 2 value. Clear? So then he'll evaluate beta, and that beta he will use where? Here. It is not a constant value. It's a value that interpolate with the blending function. Clear? What is blending function is now clear. This is a function that depend geometric configuration of the cell, means how far it is from the nearest wall, right? I will show you how this blending function looks like. Once he did that, then he found this model ideally reproduce the k epsilon result in the free stream and k omega result in the near the wall, right? So let's go how this blending function looks like. Then yes, the question came in the k omega SST model, right? In the Mentor's 93 paper, he found the eddy viscosity is k by omega. Okay, I'll come how it changed subsequently. I'll come in the 93 paper. He prescribed it is eddy viscosity is k by omega, not any scaling factor, nothing. And how this blending function looks like? This blending function is tan hyperbolic relation of some argument. That argument mostly depends upon the d, the shortest distance between the cell center to the nearest wall d, and some other parameter omega 2 k d. These are constants. Basically, they depends upon the shortest distance between the wall and the face center. He did it. Okay. Once this is known, you can calculate f1. Once f1 is known, you can calculate any property beta, any property gamma, everything, because gamma 1 known, gamma 2 known. You put gamma 1, gamma 2, f1, f2 you will calculate from the blending function based upon the, for each cell, based upon the shortest distance from the face, you will get it. Clear? He did it. 93 paper, Florian Mentor did it. Okay. Then subsequently he did the correction. Okay. He did the correction. Okay. The eddy viscosity. Okay. Wilcox also derived a similar version of the k omega turbulence model. Later in 2008, Wilcox derived a similar version of the k omega turbulence model, but his eddy viscosity is k by omega tilde, where omega tilde is the maximum between computed omega and 7/8, the strain rate by beta star. Wilcox also in the later stage developed similar version of the model that Mentor has developed, right? Then subsequently Mentor in the 94 paper did a substantial revision of the model. 93, his eddy viscosity was prescribed k by omega. Okay. In the 94 paper, Florian Mentor changed this nu t is maximum of a into omega. In capital omega, this is the mean strain rate mean vorticity tensor into another blending function f2, right? A1K divided by maximum of A1 omega into A1 F2, right? If it is maximum is A1 omega, this is exactly K by omega. If maximum is this is vorticity, mean vorticity, then it will blend again another function F2 times mean vorticity. What is this F2 looks like? It is again the tan hyperreal function of argument 2, and argument 2 function looks like this. Clear? So from his 93 paper to 94 paper, okay, what he changed? He changed the how the eddy viscosity is calculated, okay, and also he limited the production. He found the production is excessive. There is some false production kind of thing. To limit that one, he limited the production. So first he find the eddy viscosity production, just traditional way we are finding the turbulence production. The minimum between 20 beta star, rho omega k, and production based upon the eddy viscosity. That model means here into the gradient of the velocity. That production, whichever is mean, that was the limited production that is used in the model. And this version of mentor model is known as K omega SST model. Okay, K omega SST model. So this model is Mentor's K omega SST model, widely used in the turbulence community. It is well respected because it blends a function that goes from the wall to somewhere in the core, and it reproduces the ideal results equivalent to K epsilon at the core and K omega at the wall, right? Again, 2003, Mentor did a correction again in his paper. What is his paper? Here, to calculate the omega, he used the mean vorticity, average vorticity. He found in the gas turbine research, these are not invariant. Okay. Then in his 2007 or 2003 paper, I will come, he replaced those vorticity by mean strain rate. Yes. 2003 paper. Mentor in 2003 paper, okay, he replaced this vorticity to omega ij root over, he replaced those by mean strain rate, because he found strain rate is invariant to coordinate rotation and all, while the vorticity is showing variation with respect to coordinate and all. So in a decade, he changed this thing. So later, then nu t is equal to maximum A1K when SF2, where S is this one, and change there is a CD KW. This is another coefficient, 10 to the minus 10 and maximum between these two, right? So in the month of May, we had a conversation with Florian Mentor. I have fortunate enough to had an interaction with him. I asked him, sir, what led you, how you think to replace that mean vorticity with the mean strain rate over a decade of time? He just with a smile, he told, yeah, with a decade of time, he did a lot of modeling work for some aerospace application. He found with the coordinated rotation, the vorticity does not, mean vorticity is not showing the invariant property, rather than the mean strain rate is showing invariant property. So I got the data from horse mouth directly from the face of Florian Mentor. I had it. So that's why this is the final form of the K omega SST model that is implemented in ANSYS Fluent, Code Saturn, or any open form, any other software, based upon his 2003 paper, not 93 paper, 94 paper. Now it is clear what is SST model. It was developed by Wilcox. He forget the cross diffusion term. It was giving excessive of sensitivity to free stream. Then he introduced the cross diffusion term, but constant coefficient. Then Florian Mentor thought to blend it, just like it will ideally reproduce the K epsilon at the free stream and K omega at the solid wall. He proposed a blending function F1. He proposed that F1 depends upon again mean vorticity. In 94 paper, he did some correction, and final correction in his 2003 paper did it, where he replaced the mean vorticity with the mean strain rate. And this is the final version of the K omega SST model. Now, if you open any commercial solver, it will show you K omega baseline model, that is the Wilcox baseline model is there. K omega SST model, K omega Wilcox model. All these models are there, variant models are there. There is nothing thing that which one is better, which one is not better, but because of the lot of validation in most of the situation, K omega SST is default turbulence model for some of the solver like ANSYS, Fluent. They are the default turbulent model. Okay. So how this is a NACA aerofoil. Okay. Over the aerofoil, the flow separation is happening. Okay. The BSL, the baseline model. This is a standard K epsilon model. This is only the Wilcox K omega model. When the DNS data was evaluated at different chord length, okay, at different length of the chord, when the DNS data was compared with the experimental data, the K omega SST is found to give a good matching with the DNS data, where the standard K epsilon, the K omega, they fail to predict the separation, boundary layer separation. At this location, you look, the boundary layer is getting separated. Okay. There in this separation location, you will find the flow is coming. This kind of eddy structure is forming. This is aerofoil. Fishing. Oh, my drawing is. Once the uniform flow will come and hit it, so it will pass like this. So here you will form some eddy structure. You will find there is some separation, flow separation from over here in this region, right? The all other model, the standard K epsilon model, the K omega baseline model, they fail to predict the separation properly, while the K omega SST predict it properly, right? So like that, many cases K omega SST reproduce the results quite well. So that's why some of the solver put it as a default model. Okay. Again, the boundary condition for K, boundary condition for omega, we need it as decided, discussed earlier. K omega model is a by default low Reynolds number turbulence model. It integrates omega up to the wall. What boundary condition it uses at the wall? It uses the Neumann boundary condition for the omega at the wall. At the wall, the gradient in the wall normal direction for the omega must vanish. Near the wall, the gradient of the K must vanish. It is this condition is also used in the K epsilon model, but K omega model they integrate up to the wall. So by default, the K omega model is a low Reynolds number model, right? But again, the commercial solver they use some wall function for K omega also, because it is also not possible always to create the fine mesh near the wall. If your wall mesh is sufficiently fine, by default these two boundary condition is going to be used. If it is not, they will find some appropriate wall function, then they'll do the wall function approach. And some open source software like CodeCytron, there is a prohibition to disable the wall function in K omega model, but in ANSYS Fluent you cannot. By default wall function will be there. It's a K epsilon or K omega, wall function will be there. In my last interaction with ANSYS Fluent, I asked them, okay, please allow the user to disable the wall function for any of the moment if you want to integrate up to the wall or want to do some R&D activities. So I don't know, maybe in future version they will give or not, but in CodeCytron, you can completely disable the wall function. Sometimes disabling the wall function reproduce good result. Okay, you can do a lot of R&D by avoiding the wall function. Okay, the wall function sometimes artificially triggers or induce the turbulence. So disabling the wall function sometimes avoid those artificial turbulence, right? So you can perform. So in the open source code, I think this one open form also, you may have see how these models are implemented. You can disable the wall function and work on it, develop further model development. These are all pure CO model for pure CO driven flow. If there is a buoyancy driven flow is there, there is an additional production term due to buoyancy. To model that one production term, you need a lot of other information. You may need to solve additional partial differential equation. So someone was asking about Prandtl number. Okay, this turbulent Prandtl number is again another scaling factor like eddy viscosity. Eddy viscosity by turbulent Prandtl number, they define turbulent Schmidt number kind of thing. So turbulent Prandtl number, some code it is constant 0.8, 0.85, 0.9. For some code it is a variable that they have the additional equation to define the turbulent Prandtl number. So based upon the situation, what kind of fluid, turbulent Prandtl number also changes based upon the thermal Prandtl number in some model. So there is not any universal law to find out this empirical coefficient. These are based upon the experimental matching or validation. So then that's why for a user it is very hard to tell. Even if you ask me which model performs best, I will remain silent. I will not answer it, because the thing is there is not any single model that performs best. Based upon the scenario, based upon the application, you will find a particular model is working, or maybe all models are failing. Right? So it's again heuristic approach. You have your prior experience to know which model works, which model fails. There is not any shortcut way. Okay. Then again, how to find in the, as we tell already, you have the enhanced wall treatment kind of thing. In the K epsilon boundary condition, for the epsilon we need Kp and omega p to calculate the wall correction, wall boundary condition. So this is how the Kp and omega p are calculated. For the omega p, they are calculated based upon the nu by distance from the shortest distance from the wall. There is a viscous omega, there is a logarithmic omega. So based upon that, the shear velocity will be calculated. Once shear velocity will be calculated, y plus will be calculated, right? So this is what we come to the end of the session on K omega modeling. If you have any additional doubts, please feel free to ask. If you have any doubts on K omega model, please feel free to, yes. Okay, so this is the wall, right? This is the solid surface. If wall is not there, what will happen? There will be only uniform flow. For uniform flow, there is zero shear. There is no shear. The gradient must vanish. Who is providing the shear? Well, so what this model is doing? K epsilon at the wall, K omega at the thing. So the what information while blending based upon the shear stress information is transmitting over wall to the region. So that's why they name it shear stress transport. Yeah, yes, based upon the magnitude of the shear stress, the blending is getting place. If the shear stress is vanishes somewhere, then it is ideally behaving like K epsilon model. If it is the shear stress is high somewhere, it is behaving like K omega model. The phi term is the coefficient, any coefficient. Basically the blending function is dependent on what? The blending function dependent on the blending function f1. If you look, the blending function mostly depend upon the parameter d, that is the distance from the wall. The more is the distance, less is the shear stress. If short is the distance, maximum is the shear stress, right? If I go close to the boundary layer, I'll get the maximum shear stress. If I go far away from the wall, shear stress will vanishes, right? So basically the f1 function, it depends upon the other parameter which are mostly constant, and that depends upon the wall normal shortest distance from the nearest wall, right? So once you get the f1 function, okay, this f1 function is used to blend the parameter. That parameter from the wall, what's supposed to be the parameter value? What supposed to be parameter value away from the wall? Okay. So if it is near to the wall, this will take more value from the sigma k1. Suppose in the phi, this phi is a generic variable. This may be this variable, this may be beta 1, this may be gamma 1, this may be sigma w1. So once you find out the f1 value, then you will put f1 into sigma k1 plus 1 minus f1 into sigma k2 to find out what is sigma sigma k, and this sigma k will be used here. Sigma k. Yep. Here it is not a just constant, it's a variable. The variable value depends upon the phi. Now it is clear. So indirectly this blending function indicates the strength of the shear. In the free stream it is vanished, in near the wall it's a maximum. So that's why the Florian inventor named it as SST. Clear conceptually? Any other question? Any other question? Any doubts? Thank you for your attention. So let's meet in the afternoon around 3 o'clock or 3:30. When is the next session? 3 o'clock, right? Let's meet at the 3 o'clock. We'll start large eddy simulation. The lecture note on last large eddy simulation. That will be the final talk of this 2-day workshop. Then in the 4 to 6:30, we'll do some hands-on training in ANSYS Fluent regarding the RANS and the LES simulation, right? And make sure to have your geometry file, mesh file ready. We'll run the cases with different RANS model. We'll see how K epsilon is behaving, how K omega is behaving, and how LES is behaving. We'll compare it in the lab. Thanks for all your attention. Thank you. See you again.